All right, guys. This is the Chapter 6 review. So if you're missing from class right now, I hope you're watching this to study, to prepare your test. Again, test is going to be on day 1 of next week. That's for you guys. It's an 8 week, so you're going to start first period of the week with a test. Okay, so to study, you want to review this, obviously. Watch this video. And also, I assigned some, finish any late delta, 100%, guys. That's due on Monday. And last, maybe do that optional delta if you're done. Okay, so those are the 3 things. So this is your review practice test. Do any late delta, and then there's the optional delta. I will be in my room at on Monday morning if you have last minute questions. Okay, I'll be here around 8:20. Okay. All right, let's get started. So we're on 6.1. This is where we began. You already had a quiz on this. You would want to, let's review this quiz as well. If you have it, please review it. First thing, 0 exponent. Anything to the power of 0 is 1. So 4 to 0 is 1. X to 0 is 1. Anything to the power of 0 is 1. Got it? Okay. Negative exponent. For any integer n and any non-zero a to the negative n is the reciprocal of a to the n. What that means is a to the negative n is 1 over a to the n, and 1 over a to the negative n is a to the n. So here, 5 to the negative thirds would be 1 over 5 to the thirds, and 1 over x to the negative thirds would be just x to the thirds. X to the third. Let me zoom in a little bit. Okay? All right, product of powers. So when the base is the same, we're able to combine the product of powers by adding their exponents. So for example, all right, a to the m times a to the n is a to the m plus n. So 4 to the 3 times 4 to the 5, that would be 4 to the 8, because 3 plus 5 is 8. 5 plus 2 here, x to the 7. Okay? All right. Next one, quotient. So when we divide, same rule. We divide, base is the same, you subtract. 8 minus 5 is 3, 4 to the third. X to the third over x to the 5, that's x to the negative 2, because 3 minus 5 is negative 2, which would be the same as 1 over x squared, right? When we write the answer, the final answer, you want to write it in positive exponent form. Okay, when we've got a power to a power, we multiply the exponents. So here, 3 times 5, that's 15. So 3 to the 15, 8 times 4, that's 32. 8x to 32. Same rule applies if you had a product to a power. Each exponent inside the product gets multiplied by the power on the outside. So remember that there's an imaginary 1 on these x and y. All right, 3 times 1 is 3, 3 times 1 is 3 as well, so it's x to the third, y to the third. Same thing here. 2 times 1 is 2, so this would be 3 squared. X to the 5 times 2 is 10. 2 times 2 is 4. So again, each exponent on the inside of the product is getting multiplied by the exponent on the outside. Okay, last one, it's the same rule, it's just a division instead of multiplication. This would be x to the third over y to the third. And then on bottom here, 3 to the third, y to the 15 over y to the 6. All right. Any questions on that first page? Okay, cool. So again, to get practice, look at delta, right? Practice on delta. I'm going to pull problems from there, right? So that there's going to be no surprises. Just look at the delta problems. All right, 6.2 is all about radicals and fractional exponents. Remember that this is a radical, right? This is the radical symbol. And whatever is on the inside here, that's the radicand. You don't necessarily need to know that from vocabulary, but it's helpful. And remember that x to the m over n equals the n root of x to the m. So again, the denominator is the root, and the numerator is the power.
Bless you.
Thank you. Okay. All right. the square root of 50. So this is simplifying square roots. So remember, if I give you a square root, like the square root of 50, and I say simplify that, this is wrong. Okay, you know this, rewrite the fractional exponent. I don't want you to do that. I want you to simplify the radical. To simplify the radical, you find the biggest square root that's in 50. So remember, the square roots are 1, 4, 16, 25, 36, etc., right? So what's the biggest one that fits inside 50? Anyway? Ricardo?
36.
So 36 fits inside 50, but when I say fits inside, I mean like multiplies into 25. Pardon? That's power. Oh, sorry. Denominator is root, numerator is power. Yeah. So this will split into root 25 and root 2, right? Root 25 times root 2 is 50. That's what I mean by fitting in. Like, it's a factor of 50. Root 25, remember, that's just 5. So the answer to this would be 5 root 2. Does that make sense? This is 5 root 2. So when we do root 72, yeah.
It says what the thing on the paper says, rewrite the fraction.
The fractional exponent here?
Yeah.
Yeah, ignore that. That's wrong. That shouldn't be there. This should be just simplified. Root
Yeah,
7.
I already did that.
Okay. Root 72. What's the biggest perfect square that multiplies into 72? It is 36. And again, you could get that in the calculator, guys. Like if you were lost and stuck, you could just do, all right, 72 divided by 25. Oh, that doesn't work. Or 72 divided by 30. Right, you can kind of guess and check your way there. But it is root 36 times root 2. Root 36 is just 6, so it's 6 root 2.
Are we allowed to guess and check?
You're allowed to guess and check to find the biggest perfect square that is a factor. Yes.
Yeah, you can guess and check.
Pardon?
When you guess and check.
Well,
When you guess and check.
I mean, we're all kind of guess and checking, but it's whether you're doing it with a calculator or whether you're kind of running through your head. Because in your head, like I'm also kind of like, oh, it's 50 divided. You know what I mean? I'm thinking about the numbers, what could work, and I'm kind of guessing, right? And eventually you get used to it and you realize, oh, like 50, yes, that's 25, right? You get quick at it. So rewriting with a radical. This is where you want to use these notes up here. X to the m over n is the n root of x to the m. So numerator is the power. Denominator is the root. So this would be the third root of 5 to the 1. Root power, third root of x to the 1. Root power, third root of 5 squared. Okay? Denominator is the root, numerator is the power. Got it? Okay. Evaluate the expression. So the fourth root of 16, again, means what to the fourth power is 16? What to the fourth power is 16?
2.
That's 2. This is 2 because 2 times 2 times 2 times 2 equals 16. That is 4. That's the same as 2 to the fourth. Okay? 16 to the 1/4 is the same as, guys, if we convert that to radical form, 4th root of 16, which we know is 2. X to the 2/3 means the third root of x squared. I can't do anything more there. 27 to the 4/3 would mean the third root of 27 to the 4th. This could be evaluated. What is the third root of 27? What is the third? So if you have a number, you can simplify it. If it's just a variable, you can't really do anything. But third root of 27 is 3. So this really is 3 to the 4th. And so 3 to the 4th is 81. So that's your answer. So again, just to kind of show that, right? 3 times 3 times 3 is 27. Therefore, the third root of 27 is 3. And then 3 times 3 times 3 times 3 is 81. That's why 3 to the 4th is 81. Okay. All right. Any questions?
No.
Okay. We're on 6.3.
Well, Mr. Joe, I have a question.
Yes.
Can I kind of like look at it for the top part or rewrite the radical? Can you kind of just like see it as kind of flipping
Sure.
the fraction?
I hear what you're saying. You're like, the root is really kind of on the top, I guess, and then the exponent is usually below that. Yeah, if that helps you, that's helpful. Okay. All right, exponential function. So recall, linear function, guys, is something like y equals ax plus b, or y equals mx plus b. And then linear, an exponential function would be y equals a times b to the x, for example, right? So in linear, we have a constant rate of change, like you have a slope of m, right? But in an exponential, you have a growth factor or multiplier each time. So let's look at an example, right? So if we look at this table, we go 0, 1, 2, 3, so we're going up by 1, but down below we're going plus 2, plus 2, plus 2. So since I'm adding the same number each time, would that be linear or exponential? That would be linear. Because when you're adding the same amount, that's a constant rate of change. That's y equals mx plus b. Over here, 4, 8, 16, 32. Do you see a pattern here? What's going on each time here? Well, the difference here is 4, then it's 8, then it's 16. If we look at the change here, 4 to 8 to 16, what did we do here? We didn't add 4 each time, we multiplied by 2. So it's times 2 times 2. So that makes this exponential.
What if it's dividing?
That's also exponential. So division or multiplication is exponential. Addition or subtraction is linear. Did you guys get that?
Yeah.
Addition and subtraction is linear. Multiplication, division is exponential. Yes, Isaac? Okay. Cool. All right. Evaluate the given function for the value of x. And like, by the way, just showing me that this was multiplication, that would be enough for you to show that it's exponential. Like when it said explain, that's fine. Like showing me that it's addition, so you know it's linear, that's fine. So we're just plugging in this number into this. So this would be y equals 2 times 1.2 to the negative 2. That would be the same as 2 times 1 over 1.2 squared. This would be hard to do without a calculator, so I'm just go ahead and do it on the calculator here. So 1 divided by 1.2 squared is 0.69, then times that by 2, we get 1.39. So if you got this problem, I would give you a calculator, right? Or you would just kind of leave it like this, right? Down here, this is something we can evaluate. This is negative, y equals negative 3 times 5 to the third. 5 to the third is 5 times 5 times 5. What's that? 5 times 5 times 5 is 125. Then times that by negative 3. We're getting into some bigger numbers here. 125. Oh dear. 125 times negative 3 is negative 375. Okay. All right, that's it though. You're plugging it in. That's the exponent is raising to that variable. We're nearly done here, guys. So I can tell you for sure, guys, I'm going to give you a problem on the test like this. I'm going to give you a problem on the test where I give you an exponential function and a table. I'm going to ask you to fill out that table, and then I'm going to ask you to sketch it, and I'm going to ask for the y-intercept, and I'm going to ask for the horizontal slope. It will not be 2x to minus 3, but it could be something else, right? So
Find the slope like the same way we did in the beginning of the year where we just like do like the subtraction.
So here's the thing. So yes, like the exponential function has slope, but that slope is constantly changing, and we're not able to draw it just by getting the slope. Linear, you can draw once you get the slope, but exponential, you have to get some points to kind of plot it. So that's why I gave you the table. So let's fill in the table. 2 to the 0 minus 3. I start in the middle. 2 to the 0 minus 3. So 2 to the 0 is, everybody? 1. So 1 minus 3 is negative 2. 2 to the 1 is
Negative 1.
2. 2 minus 3 is negative 1. 2 squared is
1.
2 squared is 4. 4 minus 3 is 1. There you go. You were ahead of me there. Then back here, 2 to the negative 1, guys. 2 to the negative 1. So important. 2 to the negative 1 is 1 over 2. So this is 1 over 2 minus 3. You could use your calculator for that, but that's negative 2.5. And then this would be 1/4 minus 3, which is negative 2.75. So we can plot these over here. So 0, negative 2, 1, negative 1, 2, 1, negative 1, negative 2.5, negative 2, negative 2.75. So we have this kind of curve. And if you had plotted 3, I'm just going to do the 3 just for the just for the consistency. 3 is at 6, 4, 6. So you can kind of see what's going on, right? We've got that nice curve, and we also have this horizontal asymptote at -3. The y-intercept was at 0, -2, and the horizontal asymptote happens at that vertical shift. It's at y equals -3. Okay. Continue. One third to the x minus 3. So same idea. Plug in the 0. We get 1 minus 3, you get -2. Plug in the 1. 1/3 minus 3 would be -2.67. Plug in the 2, you get 1/9 minus 3. That is 1/9 minus 3. That's -2.89. Going backwards. 1/3 to the -1 is just 3. So 3 minus 3 is 0. 1/3 to the -2 is 9. That's 9 minus 3, that's 6. Do you follow that okay? So when you have a fraction to a negative exponent, that becomes 3 to the 1, which is 3. Right? So when you have 1/3 to the -2nd, that becomes 3 squared, which is 9. Okay? Sketch the graphs. We're going to plot that -2, 6, 4, 5, 6, -1, 0, 0, -2, 1, -2.67. There we go. We actually have this. They have a very similar graph. The horizontal asymptote is where? What's the y value of the horizontal asymptote? So it's right here. It's at y equals -3, and the y-intercept was at 0, -2. All right. Good. All right. Growth and decay. So when you read an exponential function, you have two situations. If the number on the inside here is bigger than 1, it's a growth, right? So it's we talk about it as like y equals a times b to the x. If b is greater than 1, that's growth. If b is less than 1 but greater than 0, it's decay. So here, because it's greater than 1, let me move that up, this is going to be growth. Remember that you get the percent rate of change is like kind of the distance from 1, right? So it's, to find it, it would be 1.35 minus 1 is 0.35, which is what percentage? What percentage is that? That is 35%.
Oh yeah.
To evaluate the function where t equals 5, you just plug in a 5. Y equals 5 times 1.35 to the 5. Right? That you would do in your calculator. 1.35 to the 5 times 5, 22.4. Okay. So another problem here. Now we've got a situation where we've got a school population and it's decreasing by a certain percentage per year. Let's write an exponential function that represents it. So you could reuse whatever variables you want, but I would say P of t equals that initial population, 1,200, and then it's going to be 1 minus the growth rate as a decimal, right? So it's 1 minus r, but r is decimal. So 6% as a decimal is what? Again, remember this? 6% is 0.06. So it's 1 minus 0.06 to the t. That would be the same as 1,200 times 0.94 to the t. What's the projected population over 3 years? You just plug in a 3 for t. 1,200 times 0.94 to the third. Again, you would use your calculator for this, or you could leave it in that form, right? You would get 996.7. 996.7. Okay. All right, we're in the home straight, guys. Two minutes left.
15 years old.
I'm using my 2 minutes. We're just so close. We're on the last page. We did so well. Okay. So this is what we did. This is what we did at the end of last class. Sorry, last class when I was gone, but I made a nice video that everyone loved and watched so nicely. Hey guys, hang in there. I know we all want to leave. I know you want to leave. Can you just hang in for a second? If the bases are the same, what can you do? If the bases are the same, you just set the exponents equal each other. This is just 9x equals 7x plus 8. So, to solve that, you get 2x equals 8 or x equals 4. That's easy. This is like an easy problem, quote unquote, right? They say easy, but nothing's easy, right? But that they say that's easy. Down here, are the bases the same?
Yes.
25 and 125, they're the same? They're not.
No.
You got to make them the same. What could we? How could we make them the same? We could both make them a base of 5. You're going to make them have a base of 5. Nikki?
Well, I mean, I know it's about 245. If I don't get to Jasmine before like 245, we get slaughtered by Christian.
All right.
On recording, by the way.
Yeah.
Okay.
I do need to really get there. So. I mean, I'll wait.
Well, it is now. It's still not even time yet. It's still
Okay.
2. It's still 2:44. So I'm going to use my time.
Okay. Take your time, Mr.
5 to the 2x minus 4 equals 5 to the 9x plus 3. Then we will set those exponents equal to each other and then solve. Does that make sense? Do you guys understand this step? This is a harder problem. You make them have the same base. It takes a little while to kind of guess and check that sometimes, but you'll eventually identify that's 5. If you need to get out of here, I allow you to leave. However, if you can stay just 2 more minutes for me to finish number 3, you might benefit. Yes? Can you wait for me to finish?
Yeah, just wait.
So if you need to leave, please leave now.
Do you really need to
Wait,
leave?
since class is over, can I use my phone for something?
Can you just wait for me to 2 minutes? I'm just,
Yeah, it's fine.
okay. Yes, but yes.
appreciate that.
Yeah, okay. Bye-bye, Nikki.
Bye, you too.
All right. Let's wrap this up, guys. So this one's kind of weird. My rule is when you ever use a fraction, whenever you see a fraction, that's a hint to you to write a negative exponent. For example, if you saw 1/3, that's like 3 to the negative 1, right? 1/3 is 3 to the negative 1. So when you see a fraction, it's a hint that you're going to write some sort of negative exponent. 1/81, you probably don't know this, but that's actually 3 to the negative 4. You're like, Mr. Kelly, how would I know that? Well, if you kind of go through 3, like 3 squared, 3 to the 3rd, 3 to the 4th, you would see that 3 to the 4th is 81. Therefore, 3 to the negative 4 is 1/81. So that's 3 to the 4, negative 4 rather, and that's 3 to the x. Then you can say that x equals negative 4. So guys, if you're stuck on 6.5, look at Delta 6.5 and watch those videos and watch my old video too. Okay. All right. Enjoy your weekend.
Thank you.
I'm coming out of class right now.
Take a picture.
I don't-
On here, you're calling.